Hello everyone. In this video we are going to look at the Langmuir modified version of the Lewis theory, which is able to explain the concept of covalent bonding. Now, based on the postulates of the Lewis theory, Langmuir proposed the assumptions that could explain the covalent bonding. But Langmuir made some slight modifications to the postulates of Lewis. Even the idea of kernel that is proposed by the Lewis is being discarded. So the Langmuir basically refined the Lewis postulations because the Lewis and causal approach, right, was mainly focusing on the electrovalent bond. And Langmuir modifications have helped in understanding of the covalent bonding. But he has abandoned the idea of the stationary cubical arrangement of the octet. This is what we will call as the kernel. So in the Lewis causal approach, we have talked about the kernel. So kernel is basically you have the nucleus plus inner electrons. That is what we call as the kernel, and the outermost shell electrons, the maximum number that can be there is 8. They would occupy the corners. So the outermost will be occupying the corners of the cube. So there will be 8 corners, and in case of the inert gases, all the 8 corners will be occupied. In case of the other elements, some of the corners will not be occupied. So the kernel approach is basically the other elements, they will try to get a arrangement where they will have electrons occupying all the 8 corners of the stationary cubical arrangement. That is what is the kernel model of the atom that is proposed by the Lewis. But the Langmuir modifications, they have discarded the kernel approach. And the important postulates of the Lewis-Langmuir theory is one, if we look at the idea of bond formed by the sharing of electrons, that is what is the covalent bond. Each of these bonds will be formed as a result of sharing of an electron pair between the atoms. Say for example, we have atom A and atom B. They share a pair of electrons. Pair means 2 electrons. When they share a pair of electrons, we will say one bond is basically formed. And where do these electrons come from? Each of the combining atoms will contribute at least 1 electron for the shared pair. So means, if you have the electrons of the shared pair, one will come from atom A and one will be coming from atom B. So this is what is the normal covalent bond, and this is what is called as a single covalent bond. Sometimes what will happen is the atom A will provide 2 electrons, atom B will provide 2 electrons. In that case, we will have 2 pairs, 2 shared pairs. We are going to be calling it as a double bond. In some case, we will have atom A contributing 3 electrons, atom B is also giving 3 electrons. There will be 3 shared pair of electrons. We will call it as a triple bond. We will talk about it later, but at least each of the atoms will be giving 1 electron. And the combining atoms, they will attain the outer shell noble gas configuration. So as a result of this sharing that is happening, the noble gas electronic configuration will be attained. And how the noble gas electronic configuration will be attained? When the sharing happens, the shared pair of electrons will be jointly owned. So owned means, in common language we are saying that electron pair will be owned by both atoms, which means when we are counting the valence shell electrons, right, the shared pair will be counted for both the atoms. So 1 electron is given by 1 atom, other electron is given by other atom. But when we are counting, right, the shared pair will be counted for atom A as well as for the atom B, like this. So we will count the 2 electrons when we are counting the electrons for atom A. We will count the 2 electrons when we are counting the electrons for atom B also. We will see an example, then we will be able to understand. And when these atoms are sharing 1 electron pair, right, then what we say is there is a single covalent bond. Like, if they are sharing 1 pair means we will call it as what? Single. If they are sharing 2 pairs of electrons, we will call it as a double bond. If they are sharing 3 pairs of electrons, we will call it as a triple bond. So if you look at this example, right, the formation of diatomic chlorine molecule. So each chlorine atom will have, of course, the outermost electronic arrangement of 3s to 3p5. The overall arrangement is neon 3s to 3p5. So totally it will be having 17 electrons. And in the outermost shell, we see that it is having 7 electrons. It is basically 1 electron short of the octet. Okay. Now we'll see how it will be able to achieve the octet by the formation of Cl2 molecule. So the Cl2 molecule formation, right, how we can understand this is in terms of the sharing of a pair of electrons between the two chlorine atoms, because here the transfer of electrons will not happen. So why? Because the transfer will be happening from an electron which can lose, which can, so an element which can lose electron towards the element that can gain electron. But in this case both are chlorine only, right? So they don't have any tendency to gain and lose, in the sense, one chlorine cannot be losing electron towards other chlorine. So the electrovalent bond theory will not be valid here. So we will see how the sharing will be able to make each chlorine to reach octet. So how the sharing will happen? Each chlorine atom will be contributing 1 electron for the shared pair. So look at it, chlorine 1, let's call it as chlorine 1 and chlorine 2. Okay, chlorine 1 has got 7 electrons in the valence. Chlorine 2 is also got 7 electrons. Now chlorine 1 is giving 1 electron for the sharing. Chlorine 2 is also giving 1 electron for the sharing. So this is becoming the shared pair. Now what is the remaining electrons of chlorine 1? 6. What is the remaining electrons of chlorine 2? 6. Now what we said, when we are counting the electrons of chlorine 1, we will count the electrons in the valence shell of chlorine 1, its own electrons, 6 electrons, plus we will have to also count the shared pair for chlorine 1. Got it? Now look at the total count, it is what? 8. That is how the chlorine is able to reach octet. Now let us look at the story of chlorine 2. Chlorine 2 means it is also having its own 6 electrons, and we will be counting the shared pair for chlorine 2 also. That is what we means by the shared pair jointly owned by both the atoms. It is going to be counted for both the atoms. You can see here also, this is getting what? 8 electrons in the outermost shell. So this is how the diatomic chlorine will be able to make both the chlorine atoms to reach the octet. So we see here the method is different from the electrovalent bond that we discussed in the case of the Lewis and Kozal approach. And between any two atoms, right, we can either have a single bond. Single bond is what? The bond produced by the sharing of one pair of electrons. Like if you talk about methane, right, what is this called as? Methane. So methane, carbon is bonded to 4 hydrogens. Okay, so here I am representing it in a diagrammatic manner, isn't it? So we will learn we may have another video on this. So we will be calling this type of representations as the Lewis structures or Lewis dot structures. So we'll learn about it later. But yeah, you can see that the carbon, right, is forming 4 single bonds, one with each of the hydrogens. That is what we call as single bond. Even the chlorine, diatomic chlorine, right, what we saw, there is a sharing of one pair of electrons between chlorines. That is what we call a single bond. We have a double bond. Double bond will happen because of sharing of 2 pairs of electrons. Okay, so if you have each of the atoms that is contributing 2 electrons, like say for example atom A is there, it is giving 2 electrons, atom B is giving 2 electrons, we will be forming 2 shared pairs. That is what we will be calling as double bond. So we have examples like CO2, right, is an example. So in CO2, each carbon will form a double bond with oxygen. So carbon will be forming a double bond with one oxygen here and another oxygen on the other side. Now why carbon in this case, right, carbon is able to form 2 double bonds. Each oxygen is able to form only 1 double bond, isn't it? So why carbon is able to form 2 double bonds? Why oxygen is only able to form 1 double bond? We will be able to understand the reason for this when we talk about the concept of covalency. So we'll discuss about this in the video itself. Then we can have a triple bond. So if you have each of the atoms contributing 3 electrons, totally we will be having what? 3 shared pair of electrons. So example for this is diatomic nitrogen. So in N2 molecule, right, there will be triple bond between both the nitrogens. And you may have a doubt, why not 4, why not 5? The maximum number of bonds between any two atoms, right, will be only 3. Now the reason for this is, if we look at the electron repulsions, or we can call it as electron pair repulsions. So if you have three shared pairs, right, if one shared pair is along the x-axis, other shared pair is along the y-axis, the third shared pair is along the z-axis, between two atoms, right, atom A is here and say for example atom B, x-axis is taken, y is taken and z is also taken. So the repulsions that will exist between these electron pairs, right, will not easily allow another pair of electrons to be shared between the atoms. So this is one of the explanations to why we can only have maximum 3 bonds between any two atoms. Now we'll talk about the concept of covalency. So this is what will tell us why that carbon is able to form 2 double bonds, whereas oxygen is only able to form 1 double bond. Okay, and similarly in the case of N2 molecule, we have seen nitrogen is able to form a triple bond, whereas in case of the diatomic chlorine, between two chlorines there are how many bonds? Only one single bond. If you look at diatomic oxygen, right, between both the oxygen atoms we'll have double bond. So why different atoms are able to form different number of bonds? So that is what we are going to be covering in the concept of covalency. So what is covalency? We already talked about electrovalency in the Lewis-Kozel approach. Covalency is basically the number of electrons contributed by an atom of an element for sharing with other atom or other atoms. Why they are sharing? So that they can achieve the noble gas configuration. Now what does this basically mean? Say for example you have atom A. Okay, so atom A is here giving 1 electron to share with atom B. Atom B also will give 1. Okay, so that is 1 bond getting formed. Atom A, imagine, is giving 2 electrons to share with atom C. So here you are having what? Totally 2 shared pairs will come between A and C. Atom A is also giving 1 electron for sharing with say D. Now let us look at it. If you talk about the covalency rate of atom B is sharing how many electrons? It is only sharing 1 electron. Okay, so it is forming what we call as a single bond with atom A. So covalency of B, right, B will be equal to what? 1, because it is giving 1 electron for sharing, which means it is forming 1 bond. And what about covalency of C? C is giving 2 electrons for sharing. Thereby what we see, there are 2 bonds. Rather we know the 2 bonds are given only for A. That's why we call it as a double bond, isn't it? So double bond means there are 2 bonds. So covalency of C in that case will be what? 2, because it is giving 2 electrons for sharing and it is forming a double bond. Now what about the covalency of D? Covalency of D will be, D is giving 1 electron for sharing with A, it is forming a single bond. So covalency of D is 1. Now we will come to the covalency of A. So what will be the covalency of A? It is giving 1 electron for sharing with B, 2 electrons for sharing with C, and 1 electron for sharing with D. Essentially it is forming a single bond with B, a double bond with C, and a single bond with D. What is the total number of bonds formed by A? It is what? 4. How it is coming as 4? Here we have a single bond, here we have a double bond. Double bond means we have to count it as 2. And here we have a single bond. Totally the covalency of A will be equal to what? 4. Now the question is how some elements, in this case, right, if you just try to apply the same logic, what we say is okay, oxygen is forming a double bond with another oxygen, means straight away what we can say, the covalency of oxygens is what? 2. Here the chlorine is forming a single bond with another chlorine. So what we can say, the covalency of chlorine will be equal to what? 1. Here we see nitrogen is forming a triple bond with another nitrogen, means what? The covalency of nitrogen will be what? 3. Here you see carbon is forming a double bond this side, double bond this side, means what? Totally we say that the covalency of carbon is equal to what? 4. Whereas oxygen is what? Oxygen is forming a double bond. This is oxygen, covalency 2. This oxygen is also forming a double bond, covalency 2. Okay, already we have seen this in the O2 example. So what we have is different elements, they can have different covalency. But how this is coming? So we will be able to understand the covalency of different elements based upon what is the group that they belong to. Okay, so if you talk about say 17th group, if you talk about the 17th group, right, 17th group is what? The halogens, which are fluorine, chlorine, bromine, iodine. So what is that they have? They have 7 electrons in the valence shell already. Okay, now if you talk about chlorine, say it is giving 1 electron for sharing, imagine, with any element, let us call it as A. Okay, so it is forming thereby a single bond. It will have its own 6 electrons remaining, and when we want to count the total electrons of chlorine, we will also be counting the shared pair. So what you see here, 6 electrons of the chlorine, 1 electrons plus the shared pair. Pair means what? 2 electrons, right? Totally it is getting what? 8. So in order to achieve the octet, chlorine has to just share 1 electron, or chlorine has to form 1 bond. That is what we'll see to achieve the octet. So the covalency of chlorine, right, the number of bonds it has to form to reach the octet will be just what? 1. So if you look at the number of valence electrons of the 17th group, now what is the number of valence electrons of 17th group? It is 7. So the covalency in this case will be what? 8 minus number of valence electrons. 8 minus 7 is equal to what? 1. Okay. Now we'll take another case. So let us talk about the 16th group element. 16th group elements are what? Oxygen, sulfur, selenium, tellurium, polonium, isn't it? So we'll talk about a 16th group element. Let us say oxygen. We can even take sulfur. Okay. Let us take oxygen. So oxygen has got 6 electrons in the valence shell. Okay. And if it is forming, say it can form single bond with atom A and another single bond with atom B. Okay, so what we see here is oxygen is giving 1 electron for sharing with B, 1 electron for sharing with A. Okay, so now after giving 2 electrons, what is the number of electrons remaining with oxygen? 4, right? 6 electrons are normal count, valence electrons. 2 are given for the sharing, 1 for A and 1 for B. Okay, now remaining will be what? 4. If you want to count what is the total number of electrons of oxygen in the outermost shell after this sharing concept, we will count the 4 electrons of oxygen, its own electrons in the valence shell, plus this is one shared pair, this is another shared pair. So 2 electrons plus 2 electrons. Totally what is the number of electrons? 8 electrons. Thereby oxygen is able to reach octet by forming 2 bonds. So if the 2 bonds are formed with same element, means it will become a double bond. Like oxygen can form a double bond with oxygen. It can form a double bond with nitrogen. Oxygen can also form a double bond with carbon. We have seen in the, of course, this is not the full molecule, but we have seen this happening in the CO2, isn't it? So what is the covalency of oxygen we see here? It is 8 minus, what is the number of valence electrons of oxygen? 6. 8 minus 6, which is 2. Okay, so what are we getting? We are getting the covalency as what? The 8 minus number of valence electrons. Okay, now we'll go to another example. So we'll just look at each of the groups, then we'll be able to get the overall picture. Okay, so when we go to the 15th group, next one, so we talked about 17, 16, then we'll come to 15th. 15th is what? Nitrogen family: nitrogen, phosphorus, arsenic, antimony, bismuth. Okay, so if you talk about the 15th group, what we will be able to see, we'll have the nitrogen, phosphorus, arsenic, okay, antimony, and then bismuth. But when we look at the 15th group elements, right, they'll have 5 electrons in the valence shell. So nitrogen, let us talk about it. So if nitrogen is giving 3 electrons for sharing, so let us say it is giving 1 electron for sharing with A, okay, another electron for sharing with B, another electron for sharing with C. Okay, now the remaining electrons for nitrogen are what? 2, because it is given 3 electrons for sharing, means remaining is 2. If you want to count what is the total number of electrons for nitrogen in the valence shell, you will count 2 electrons of nitrogen, its own electrons, plus 1, 2, 3, 3 shared pair of electrons. What is it? 2 plus 2 plus 2. Totally what is it? 8. Thereby nitrogen is able to achieve octet by forming what? 3 bonds. Nitrogen can form 3 bonds. If nitrogen is forming 3 bonds with another nitrogen, that is what will be making it as a triple bond. That's what will make it as a triple bond, isn't it? So the covalency of the nitrogen family elements, right, is what? 8 minus the valence electrons, which is 5. That will be equal to 3. So the common covalency that is shown by the particular group elements, right, is also what we call as the group valence. So once we cover the different groups, right, of course we'll try to look at the representative elements, because the way the D block and F block elements form chemical bonds will be a little bit different. So we'll talk about it a little later, but here we'll focus on the representative elements. Now comes the 14th group, carbon family. Okay, what is the number of valence electrons? 4 electrons. Now carbon, if it is giving 1 electron for bonding with A, another electron, so let us not use A here because already we have C here. Okay, so it is forming one bond with X, another bond with Y, another bond with Z, another bond with maybe U. Okay, so it is giving 1 electron for sharing with X, 1 electron for sharing with Y, 1 electron for sharing with Z, 1 electron for sharing with U. Okay, so all the 4 electrons are used. Now if you want to count what is the number of electrons of carbon, so it is not having its own electrons anymore because all of them are used for sharing. So how many shared pairs are there? 1, 2, 3, 4. So it means 2 electrons plus 2 electrons plus 2 electrons plus another 2 electrons, 4 shared pairs. What is it? 8 electrons. So we can see what is the covalency of carbon. It is either valence electrons, because what is the number of valence electrons? 4. We can also say it as 8 minus valence electrons, because that is also going to be 4. Here we will see one thing interesting. What is that? That carbon, it has used all the electrons available for it. It has used all the electrons available for it because it has got only 4 electrons, right? It is used all of them for the bonding, and hence the covalency of the 14th group elements will be what? It is going to be 4. Now let us go to the 13th group. What is 13th group? Boron family, right? Boron, aluminum, gallium, indium, thallium. Okay, so 13th group, when we see the 13th group elements, right, they will be having just 3 electrons in the valence shell. Let us talk about boron. Boron is giving 1 electron for X, another electron for sharing with Y, another electron to share with Z. Okay, so it has used all the electrons. It's got only 3 electrons, right? Over. Now after forming the bonds, because that's it, it cannot form any more bonds. After forming the bonds, let us look at what is the total number of electrons of boron. What is it? Here 1 pair, second pair, third pair, means what? 2 electrons plus 2 electrons plus 2 electrons. What is the total count? 6 electrons. So what we see is something which is not expected, isn't it? Why? Because we have been saying in the concept of covalent bonding that the atoms, they will participate in the sharing so that they can reach the octet structure in the valence orbit. But after forming the bonds, is the boron able to reach octet? Boron is not able to reach octet. So just keep in mind that when it comes to the drawbacks of the Lewis theory, right, we are going to talk about such kind of molecules. You know what we call them as? We will call them as less than octet molecules or electron deficit molecules. What are we going to call them as? Less than octet molecules or electron deficit molecules. Okay, so here what is the number of bonds formed by the boron? It is nothing but 3, which is equal to the valence electrons. So whatever is the valence electrons, that is the valency here. Okay, now let us look at the case of second group, because we are looking at what? Representative elements. Representative elements means what? First group, second group, then 13th through 17th. Okay, S block and P block excluding the inert gases. So let us talk about the second group. Second group means what? We have beryllium, we have magnesium, calcium, strontium, barium and radium. Okay, let us look at beryllium chloride. Okay, so beryllium, it has got how many valence electrons? 2 valence electrons. It is given 1 electron for bonding with a chlorine, another electron for bonding with another chlorine. So look at it, got only 2 electrons. It can only form 2 bonds, that's it. So we will see that here also, right, beryllium will not be able to reach octet, because count the electrons, 2 electrons plus 2 electrons. What is it? 4. It has not reached octet. So what do we call it as? A less than octet molecule or electron deficit molecule, isn't it? But Here we are discussing about the valency, right? So valency is equal to what? 2, which is equal to the number of valence electrons. Now come to the story of the first group. So first group, if you look at the elements, what are the elements? Lithium, sodium, potassium, rubidium, cesium, and then francium. Okay, so we have lithium. So lithium chloride, imagine. So lithium has got only one electron in the valence shell. It is just going to form one bond with chlorine. That's it. Now what will be the valency in this case? So only one bond is formed. So the valency or covalency, what we call it as, will be equal to what? 1. And you'll see one difference that in case of covalency, right, we are not going to give the plus sign and minus sign notation that we'll generally use when we talk about the electrovalence. In case of electrovalence, what we say, 1 unit positive or 1 unit negative. So we'll always talk about whether it is a positive or negative. But when it comes to the concept of covalence, we are not going to be using the plus minus concept, because after all it is what? Sharing, right? There is no loss or gain concept involved here. Okay, now let us just summarize. So first group, okay, first group, second group, then what we have? 13th, then we have 14th, then we have 15th, then we have 16th, then we have 17th. We are talking about the representative elements. Okay, so let us keep the number of valence electrons. Here what is it? 1, 2, then it is 3, 4, 5, 6, 7. Okay, what you have seen so far, that group valence. So here what is the group valence? First group lithium 1, second group 2, 13th group boron we discussed, right? They got only 3 electrons, they will form 3 bonds. 14th 4 bonds carbon. 15th what you have seen, nitrogen can form 3 bonds, right? It will reach octet. 16th, 17th. So this is what we call as the group valence. So what do we see? The number of valence electrons will actually help us in calculating what is the common or the group valence of the element. So group valence will be equal to what? It is either equal to the number of valence electrons or 8 minus number of valence electrons. So what we can easily remember is first, second, 13th, 14th. Group valence is equal to what? Number of valence electrons. 15, 16, 17th. Group valence is equal to what? 8 minus number of valence electrons. Now why are we saying the word group valence? Because the 15th group element, say phosphorus, can also form 5 bonds in examples like PCl5. So here phosphorus, right, is forming 5 bonds with each of the chlorines, or rather it's forming single bond with each of the chlorines. So which means what? Here if you have to talk about the valency of phosphorus, right, it is forming how many bonds? 5 bonds, right? So what is the valency? We will take it as 5. Okay, and 16th, if you talk about SF6, in that case, sulfur is forming how many bonds? It is forming 6 bonds, 1 with each fluorine. So what is the valency of sulfur there? 6. In examples like ClF7, chlorine is bonded to 7 fluorines. So here what will be the valency of chlorine? Here it will be what? 7. So we'll see that the p block elements, in fact when we go to D and F block elements, there it will be even more, the number of what we call as valencies that the elements can share. So here the p block elements, right, we'll say they can exhibit multiple valencies. What do we say? The p block elements, they can exhibit multiple valencies, like we have seen the examples, right? Okay, so this is what we will be able to talk in terms of the covalence. So how do you get the covalence? Covalence means some elements like the p block elements, they can have multiple valencies, but generally we can get the covalence value or the common covalence value of the particular group by knowing what is the number of valence electrons. First, second, 13th and 14th, what is it? Generally the number of valence electrons will be the covalence. 15, 16, 17th, what we see is that they can have 8 minus number of valence electrons as the covalency, or sometimes they can even have molecules where the covalency is equal to the total number of valence electrons itself. Okay, so this is about the concept of covalency as per the theory of covalent bonding from the Lewis-Langmuir theory. Okay, now while we are looking at the different molecules and trying to explain the bonding that is happening, right? We were drawing some diagrams. Okay, I even said that we will call these diagrams as the Lewis dot structures. So the Lewis dot structures, right, have helped in the understanding of bonding between different atoms in a given molecule, like how different atoms are actually bonded to each other in a given molecule, right? That is better visualized through this Lewis dot structures. So the next part video we are going to look at the Lewis dot structures.